You're okay. All right, here we go. So yesterday we were finishing up just as a reminder about what concavity looks like and how our points of inflection are located. Okay, now I want you to notice that right here, these are what I would consider to be my maxes and my mins, right? What would this minimum be considered? Absolute, but also a relative, okay? This one is a relative max, and this one is a relative min. Okay, now, about halfway between the max and the min is a point of inflection. About halfway between the max is another point of inflection. And those points of inflection are where what changes? Concavity. Okay, so, yes?
So what is like, if you see how it's an absolute, then what if the other relative min, the other one, would come all the way down to where,
Then both would be considered, because the minimum itself is the y value, so the lowest y value that this graph hits is -6, and it hits it in two places. It would hit it at -2, and if this one came all the way down, it would also hit it at -6, but at the x value of 3. Okay, so the max and min itself is the y value, but we can tell its location by telling at what the x coordinate is also.
they both be considered absolute.
Yes, yes. Okay, now, right here, okay, this can be a little bit tricky, so I want to look at this with you, okay? It says, a point of inflection can occur at one of three different places. One of three different places. So, right here, okay, we can put it right here, okay? And then I have a point of inflection right here. Now, I want to talk about this one because does my direction technically change? I am decreasing, then there's a turning point, right? There is a minimum right here. But then it's increasing, and then it's still increasing. But do you notice how right here, this is opening down, but this one is opening up. Do you notice that? Okay, so this is also concave up. So my points of inflection, okay, they can happen right here. All right, so I have three rules, okay? Rule number one is that it happens at a 0 with multiplicity 3. Okay. At a 0 with multiplicity 3. Now, I'm actually going to pull my dual enrollment notes out, and I'm just going to show this to you because I am about to introduce this concept to them. They have never seen multiplicity before like you should have with polynomial functions last year. Okay, we're going to look at it again. All right, let me see. I don't remember where I put this in their notes. Give me just a moment. Looking. Oh, okay, roots and multiplicity. So right here, okay, a graph has a multiplicity of 1 if it has an odd single power root, okay? That's where my graph just like crosses through. There's no like curving through, but it's like a linear, it crosses through. A multiplicity of 2 or an even power is when it bounces off the axis, okay? And then a multiplicity of 3, okay? It's an odd higher power. It crosses through the x-axis, but it's kind of flattened with a curvy look. It lingers near the x-axis before it actually goes through. And that's kind of exactly what this is doing. It's going through, it's kind of lingering around before it crosses, okay? All right, and then let's see, rule number 1 and rule number 3 here. I'll get to rule number 2 in just a minute, okay? Rule number 2 happens between a 0. What is a 0? Where the graph where it intersects the, not the origin, just anywhere on the x-axis, okay? All right, a 0 is the same thing as an x-intercept, as a root, as a solution, okay? Rule number 3, we can estimate a point of inflection between a 0, multiplicity 3, okay, and the closest relative extreme value. Okay, and that happened here. Okay, it was between a 0 with a multiplicity of 3, okay, and the closest extreme value. Okay, now I'm going to write down what these ordered pairs are. Okay, this is the ordered pair 0, -3. This was the ordered pair 3, 0. Okay, and if I'm averaging those things, okay, I have a point of inflection at the ordered pair. If I'm averaging my x values, 3 and 0 added together, cut in half, is 1/2. 0 and -3 added together and average, that gives me -1/2. Okay? And then there is another point of inflection at the 0 with that multiplicity 3, and that happened right there at 3, 0. Okay? Now, for graph B, okay, if I'm looking at this, all right, I've got some maxes and mins here, okay, and I'm going to say that that happens about halfway between the two of them, okay. Let's see, I'm going to plot this about right here. I feel like that's about halfway between, okay. I'm going to label that as my POI. And I see that this graph is concave down. And then at that point of inflection, it turns and it gives me a concave up interval. Okay? And this is rule number 2. Okay? And rule number 2 is that there is a point of inflection, okay, between two consecutive extremes or extreme values. In this case, I had a max and a min. Okay. I'm going to say that this maximum occurred at the ordered pair, let's see, that's -2, 5. And then right here, my minimum happens at 3. I'm going to estimate that at -2.5. That's -2.5. Sorry about that. So if I am averaging those two things, I'm going to say that I have a point of inflection at, let's see, I've got 3 plus -2 cut in half, and I have -2.5 plus 5 cut in half. So 3 minus 2 is 1, so that's 1/2. And then right here, that's going to be 2.5 divided by 2. So that's going to be a 1.25. Okay? You can write that as a decimal if you want to, the 0.5. 1/2 is fine also. So I've got 3 rules, okay? Rule number 1 is that it can happen at a 0 with a multiplicity of 3. Rule number 2 is that it happens between 2 consecutive extreme values. And then rule 3 is that it happens between a 0 with a multiplicity of 3 and the closest extreme value. Okay? Okay? All right. Now, right here on this one, okay, this one looks a little bit different, okay? I am looking at my graph, and I know that there's a max and a min here, and then there's another max over here, okay? So about halfway between these two, there's a point of inflection. I picked the 2, like right at 2 right here, because that was 0 and that was 4. So halfway between, okay? Here's 0 and here's 9. So I'm going to plot this point at about 4.5. Okay, I wrote POIs up here also, where I drew my arrows. Okay? Now, this begins by being concave down, then it turns and is concave up, and then it turns and is concave down again. Okay, now this one, these points of inflection happen by using rule number 2. Okay, you're not going to have those rule numbers memorized, okay? I just want you to know, like, there's 3 ways that we can get a point of concavity. All right, so I want to try and calculate this, okay? So this first max happened at -4, +4. This min happened at -2, 0. And then this max happened at 1, 9. So I'm trying to estimate where those points of inflection fall. Okay. You got these two. You got -6 cut in half, so that's -3. And then 4 and 0 cut in half, that gives me 2. I'm averaging my x's. That's a -2 and a -4. The sum of that is -6. -6 cut in half is 3. And then 0 and 4 added together divided by 2. Now I want to look at these 2 ordered pairs. What is -2 plus 1? -1 and -1 cut in half, -1/2 or -0.5. And then 0 and 9 cut in half, that gives me 4.5. Okay, I'm just making a note right here to average the max and min points to get your POIs. Okay. All right. Let's talk end behavior real quick, okay? We talked end behavior already just a little bit, but I'm going to make a note here that I am looking at the tails of my function, okay? All right, the behavior of a function, just the end behavior of a function describes how a function points as it moves indefinitely to the left and the right. Okay? In other words, the end behavior is what happens to the values of y as x increases with or decreases without bound. So that means as x approaches negative infinity and as x approaches positive infinity. That's the left side of your graph and the right side of your graph. Okay? Now, we are going to swap to this calculus notation, okay? This is called limit notation. The left end behavior, okay? This says the limit as x approaches negative infinity. This is the left side of my graph if I see that negative infinity, okay? Your f of x value equals something. Now, if it points up, if your tail points up, then that graph is going to positive infinity. But if your tail points down, it's headed to negative infinity. Okay? Then the right side, the same thing. My notation just says the limit as x approaches infinity. That's positive infinity. We will say f of x equals something. Okay? Or approaches something. Okay? So let's take a look at these graphs right here. Now I want to point out that anytime my graphs are cut off, okay, anytime my graphs are cut off, I want us to assume that those continue on. Okay? All right. On the left side, the left behavior verbally, I'm going to say it points up. Okay? The right behavior verbally points down. So if it points up on the left side, I will say the limit as x approaches negative infinity is that f of x equals positive infinity. You don't have to put the positive there if you don't want to. Okay, that's understood. And the limit on the right side as x approaches positive infinity is that my y values or my f of x values are pointed down, so they go to negative infinity. The limit is positive or negative infinity. All right, question. Can we ever get there? No. Okay? Just keep that in mind. All right, now on this graph, where are both of my tails pointed on the left and right? Up. What would that tell me about the degree of that function? It's an even degree. This one is an odd degree. This one is an even degree. Trying to pull back that vocabulary from yesterday, okay? All right. Both of them point up. So, the limit as x approaches negative infinity, that's the left side, is that f of x is positive infinity. The limit as x approaches positive infinity is that f of x also approaches infinity. Okay? All right, up at the top, sketch a graph with the following end behaviors. Now, on the left side, we want it to point down. On the right side, we want it to point down. Y'all, it could be something as simple as a parabola, but it could also be something that looks like this. Okay? We got different options as long as it's pointed down. for this one, I want to sketch a graph where on the left side of my graph, it's pointed down. And then right here on the right side of my graph, it's pointed up. Okay, that might be something as simple as a cubic function. Or it might have a little bit more curvature in it. Okay, we can have a whole bunch of curves in there. But either way, I'm sketching that and showing that behavior. Okay? Okay, so when I am trying to look at a function, okay, for me it's easiest to find the end behavior of the right side first. Okay? The right side goes up if the leading coefficient is positive. Okay? It's almost like it has a positive slope. It's going to increase to the right. And it goes down if the leading coefficient is negative. Like it has a negative slope that is falling from left to right. Okay? All right, the left side then goes in the same direction if the degree is what? Even. Good job. And it goes in the opposite direction if the degree is odd. Your tails go the same way if you have an even degree. Okay? So, we're not worried about limit notation here, okay? I just want to look at each function. I want to look at the degree, okay? I want to look at the degree, the highest power of each of these functions, okay? Now notice I don't have a highest power necessarily for that last one. We'll talk about that in a moment, okay? Here I have an odd degree, so my tails are going to be opposite, okay? They're going to be split. Now, my leading coefficient is positive, so that means it's going to go up to the right. So that means the right side is going to have an end behavior going to positive infinity, the left side to negative infinity. Here, because my leading my degree is even, my tails are going to do the same thing, and because this number is positive, they're both going to go to positive infinity. Okay? What about this one? I've got an even degree, but what is my leading coefficient? It's negative, so both are going to go to negative infinity. Okay? Now, this one and the next one, actually, they are not in standard form. So we've got to identify what the leading term is. Okay? You've got a negative leading coefficient for an odd power. So that means both of them are going to go down on the right. So that means it goes up on the left for both of those. Okay? Now, for this one, this polynomial is not multiplied out. So what I need to do is count how many x's I have. I have 1, 2, 3 x's. Yep. Where? This one? Because I had a negative leading coefficient, odd power. The tails are split. This one, because the negative is like a -1, that's like a negative slope, so it falls to the right. Okay? All right, so I know right here this is going to be an x to the third power function because I have 3 x's. Okay? Now, in front of each of those x's, we need to pay attention to their coefficients. Right here, there's a 2, there's a 1, and then here there is a -1. So that means I'm going to have a leading coefficient of -2. So that means this graph falls to the right. So it also is going to look like the last two. Okay? Then I'm asked to write limit statements right here. So I'm going to get those set up first. The limit as x approaches -infinity and the limit as x approaches +infinity. Okay? F of x equals, okay, tell me about my power. It's even. My leading coefficient, however, is negative, right? All right, here we go. So right here, okay, my degree is even and my leading coefficient is negative. So what does that mean is going to happen? Both are going down. So both the left side and the right side will approach -infinity. Okay? Then I'm going to get my limit notation ready for the left side. This is g of x, so I want to make sure I name it correctly. Okay? The limit as x approaches -infinity, the limit as x approaches +infinity, g of x equals something. Okay? Bless you. Now here I have an odd degree, which tells you your tails are split, but my leading coefficient is positive, so that should mean that it goes up on the right. Therefore, it goes down on the left. Okay? Any questions about that? Okay. All right, so listen, I am about to hand to you your 1.4 practice. Okay? All right, hush, I'm still recording. Okay? You must use your time wisely in class. If you are going to socialize like you did last time, it will all be due when you first come to class tomorrow. Use your time wisely. If you put your heads down, if you pull your phones out, that is you not using your time wisely. You may use a graphing calculator, you may use Desmos, but I am running GoGuardian every single day it's running, whether I'm here or not, and I have a report. So when it comes to the end of the semester, if you are sitting at a 69.4, a 79.4, an 89.4, I am looking at those reports. I am looking at whether or not that you did anything extra in order to see if you deserve that 1/10 of a point to round you up. Clear?